let's do this thing. The floor is yours. Questions? Yes.
You go over this exam 2022 part 1 E.
And 2022. Okay, so part E and F. Suppose A is by the way, how many eigenvalues do you expect this to have? 6. Do they have to be real? Not necessarily, but you should have 6 eigenvalues counting multiplicities if you're taking complex ones as well. And I know for a fact that -1, 2, and 3 minus 2 are eigenvalues. Okay, I'm gonna do D before I answer your questions. First question, there are 4 eigenvalues. Where are the other 2?
The conjugate of the terms.
Because that's a real matrix. So eigenvalues have to come in complex conjugate pairs. So if you've got an I, you have to have a negative I. Right? You've got anything that's conjugate. If that had been C 6 by 6, you couldn't answer the question. Because if it's over C, you don't have to have complex conjugate pairs, right? I mean, over C. The eigenvalues here are I and 2, right? But that's not a real matrix, it's complex matrix. But here, you have to have the complex conjugate, right? So, part E says, what is the determinant of this matrix? How do I figure it out? Anybody?
-2.
Oh, I don't know. Let's see. How would I figure it out?
Multiply the eigenvalues.
There you go. The determinant of A is the product of the eigenvalues. So in this case, it should be -1 times 2 times I times minus I, 3 minus 2I, 3 plus 2I. And this is -2. That's -2. That's +1. And this mess is 13. The term is -26.
That's assuming it's like that.
No, doesn't matter. If you have any matrix, you have any real matrix, its determinant will always be the product of its eigenvalues. Over which fields is this matrix diagonalizable? In either.
Complex.
Somebody says triangle is complex. It is. How do you know?
It has a
That's
complex.
complex.
What's the name?
It has complex eigenvalues.
Right, but, right, but just because it's got complex eigenvalues, I mean. Well. That has complex eigenvalues, the eigenvalues are one, which is a complex number, it's not diagonalizable. There's something else about the eigenvalues, I don't think you quite said enough.
They have imaginary parts in the eigenvalues.
And that still might not be good enough, what's true about all the eigenvalues? What do you, oh, so let me take you to a more basic question. What is the main thing that you have to have for an n by n matrix to be diagonalizable?
And different distinct eigenvalues.
In linearly independent eigenvectors, right? That's what you have to have. Now, I didn't figure out any eigenvectors here, but there's a little clue here. You have 6 different eigenvalues, and that means you have 6 different linearly independent eigenvectors. So, yes, 6 distinct eigenvalues means you have 6 linearly independent eigenvectors. Now, be careful, just because you don't need 6 distinct eigenvalues to have linearly independent eigenvectors. Right, but for sure if you do. How about over the reals? No, why? No, eigenvalues. If it was diagonalizable, you need the eigenvalues on the diagonal, and they're complex, and you can't do it. Let me give you a quick example here. This matrix has the identity matrix has this characteristic polynomials was only eigenvalues. Right. But look at it. I bet it's diagonalizable, right? Because it's already diagonal. All right. But this also has 2 linearly independent eigenvectors. So just because you don't have 2 different ones doesn't necessarily mean you can't diagonalize it, right? So the key point is the eigenvectors. But here we could shortcut it. So Victor, did I address your questions? Okay. Yes.
Where's 18 question 1?
It was 18 question.
From this view.
Is 18. Oh, this is more about the similarity. So, okay. By the way, is this problem that you're looking at? This thing about similarity?
Yes.
Okay. What do you say B is similar to A? I'm a lazy man. I don't want to write this similar to every time. So I'll put that little squiggle there. It needs to be similar to A. Okay. if there is anybody in the environmental matrix B, what's that? Okay, so I asked you 3 questions about this. This is a concept in mathematics, a similarity. And what similarity is it mimics being equal. It's not quite as strong, like, and it satisfies 3 things. First, y is a similar to so what does it mean for B to be similar to A? It means I can find an invertible matrix and I can relate the 2 like this. Why is A similar to A? The burden upon us is to find an invertible matrix that makes this work. Can anybody think of one? Can you identify one?
Yeah.
How about that? Right? Right, so A is similar to A. If B is similar to A, show A is similar to B. B is similar to A means but now I've got to write A that's what the burden is, right? I've got to find another invertible matrix so that A is similar to B. What should I do? Oh dear, help me. Yes.
Multiply by P on both sides.
Okay, great. So let's just massage this. I've got this right here. Hit this sucker on the left with P. I get that. And now on the right, P inverse. So A is equal to P, the inverse. Right? Now, for those of you that might be bothered a little bit by the fact that this started with P inverse, it maketh no difference. All you need is an invertible matrix. And in fact, I can write this. How about this? This is P inverse. Inverse the P inverse. And so my new matrix is P inverse, right? The inverse of P inverse P. And the last thing that I have to do is show that suppose B similar to A and C is similar to B, show C is similar to A. Everybody feeling it? So what does this mean? Well, this means that B and what does this mean? If C is similar to B, what does that mean? Yes.
It's the same relationship but with a different matrix.
Very good. Might not be the same P here, might be some different invertible matrix. Everybody okay with that? Now, what I'm gonna do is I'm gonna take what B is and replace it inside here. Am I okay with that? So, the lucky name. Is PQ. Numbers. So now my new invertible matrix is P times Q, right? Everybody okay with that? Similarity mimics the stronger version of equality, right? How is this? These are all of these properties are satisfied by equals, right? If you have equality, certainly anything is equal to itself. If B and A are equal, then A and B are equal, right? And if A and B are equal, and B and C are equal, then A and C are equal, right? But you don't have to be equal. I can do an equivalence relation on this class here. I'm gonna say the two people in this room are similar if they are sitting on the same side of the classroom, right? You're sitting on the same side of the classroom as you are, so you're similar to yourself, all of them, right? So you two are similar because you're sitting on the same side of the class as him, and you're sitting on the same side of the class as him, so A is similar to B means B is similar to A, and it's transitive. You two are on the same side of the class, you two are on the same side of the class, so you two are on the same side of the class. This is important in mathematics because equivalence relations often have they group the sets into things that are very similar. And similarity here with matrices is if you have two matrices that are similar, what do we know about them? We know that they have the same eigenvalues, they have the same characteristic polynomial, they have the same determinant. They don't necessarily have the same eigenvectors. That's a little bit different. But the matrices basically are representing the same linear transformation with respect to different bases. So their similarity of matrices is very important that way. Okay, questions? Yes, sir.
Question 2 from quiz 20.
Question 2, quiz 20. Okay, so understand last 20 and 15. So I'm gonna break this down actually. The first thing I'm gonna do is I'm going to first find the eigenvalues and the eigenvectors for this. Right, that's a good kind of first step because this is sort of asking about rewriting a transformation. And from this, I get everybody, is everybody comfortable with that? Those are the eigenvalues you get. Now notice these are complex eigenvalues. So I'm using this theorem at the end of that section that we have on complex eigenvalues. I think it's section 5.5, but it's the one on complex eigenvalues. So we need to find the null space of here minus 12 plus 4i 8 minus 20 And right, I'm searching for the eigenvectors, I have to do this, right? And I expect to get complex ones. Yeah, this is kind of obnoxious. Now, I am going to go through this computation here, but one thing is, I can almost redo this. I know for a fact, this has to have little zeros when I reduce it. It has to, unless I've screwed up my calculation with the eigenvalue. Right, but let's go through it and see what happens. The one thing I'm gonna do is I'm gonna turn both of those elements in the left column into ones by dividing out. So I'm gonna divide the so I'll divide the bottom row by -20. And that's going to give 3 plus I over -5. Right. And I'm going to divide by whatever that thing in the top is, -12 plus 4I. Actually, I should have taken 4 out of this. Two over -3 plus 2I. Oh, -3 plus 2I. Am I agree with that? Doesn't look like those rows are the same, does it? But they are. Right? In fact, this is kind of a good exercise here. I understand this thing a little bit better than the other one because this has got like this 3 plus I in the bottom, right? So let's fix this. And I'm gonna fix this by multiplying top and bottom by the same thing. What's my logic here? What's gonna happen to that bottom thing? It's gonna kill the imaginary part of the the top. I'm gonna have -6 minus 2I. Right. In the bottom, I'm going to get 9, 10. And then I'm gonna get plus 3I minus 3. The I part is history. And what do I get? If I divide out by say 2. How about that? I thought I'd work that out, but convenience, right? So what I get is this. And there we go. This is my, well, it looks like row reduced echelon form. I've got one free variable, one basic variable. So basically my equation is this. So my eigenvector should look like well, I haven't said much there. And Everybody okay with that? Now, there's a trick that you can use that. And we leave it up here. So. And let's let PN bars in. Let me figure out what PN bars is here. Remember this is 0, 3. What's that? This much of this. Let's see. If you do. Look at this here. Let's kind of go through this. The first meeting is one more things. We're getting maybe 20. We get 10. Minus 45, minus 60. Right? That's because that's a minus 50. Yeah, yeah, that's right. Okay, so I got this right. That's gonna be minus 45, 60. 40 minus 45. And this should be my covenant matrix that is both that's a rotation and a scale. Let's cross our fingers, shall we? This is going to be minus 12 and 15 is 3. It's going to be minus 4. This is going to be 9 minus 5. And that's going to be 3. So the basis. The first thing I asked you, it should be the columns in the way I've written this, P and this. Because what we have here is we have let me call this matrix here R. And that's what we've got here. Where in that theorem, the matrix takes on A minus B, B, A, or the eigenvector is A minus B, I. And let me kind of draw you a diagram of why this is the basis. So what we have is a linear transformation. From R to R. And that transformation is originally A, say in standard coordinates. Now I wanted a basis B, where the matrix is in this form R. It's the B coordinates. Now, how do you get from, well, how do you get from B coordinates to standard coordinates? Well, it's the matrix that makes up your basis, which I claim is this. So if basis is 3/5 1, 1/5 0. The matrix that changed B coordinates to standard coordinates is this matrix here, B. Which I actually call well, no, I'm gonna, see, this is yeah, this is so I call the inverse. There we go. So I've got the notation back. P inverse should take B coordinates to standard, right? And what takes standard to B coordinates? The inverse of this, which is P, right? And so what you have here is, let's see which way did I do this. If I do right, so to do A, going this way is the same thing as changing the doing A should do. So doing A should be doing P. Oh, yeah, that's right. I should do first. And from here to here, it's the same as following this path. Like to get this matrix that's here, you first change your coordinates to B, you do your R, and then you change your coordinates back. Right? So in order, what that means is start with your vector P, change it to R coordinates or B coordinates, then do R, and then do P inverse. And that's the same equation as we have right here. So even no, so in other words, so the basis change that we need is exactly this is the basis. So this is very similar to that stuff with the diagonal matrices, except these matrices are partial rotations, and they this matrix doesn't have any real eigenvalues, and so it looks a little bit different, but basically the formulation is the same as for diagonal. Now, the next question asks, what's the scaling and what's the angle? Well, so we discussed how to break this down. Let me ask you this. Can you tell me what the scaling is for this? This will kind of, let me show you how to kind of discover this. This comes from the eigenvalue 3 minus 4i, correct? Tell me what's the length of that matrix? This is a 3, 4, 5 drive. So my scaling should be a 5. Pulling out this is essentially pulling out a factor of 5. Everybody agree with that? So my scaling. That's basically multiplying by 5. I agree with that. What's the rotation? This matrix doesn't do rotation. And the reason I know that, what happens when you take 3/5 squared plus 4/5 squared, you get 9/25 plus 16/25, which is 1, right? So there's no size change in this all, it's pure rotation. And it's actually a form of this matrix we discussed a lot. So oh, I would have changed it better. So what this, with respect to that new basis, this matrix, the original matrix, basically what it does is it rotates everything by whatever that crazy angle is, and then it scales it up by a factor of 5, right? And that's easier to understand than the original matrix, right? With all the crazy random numbers in it, right? Okay, any questions on that? Others? Yes.
Number 3 on summer 2018 exams.
Okay. Exam.
4.
The fourth one, okay. So. So you have the following. And we assume that we found the characteristic polynomial. Okay. Compute the characteristic polynomial. And after my computations are done, I get this polynomial. First question, what is n? What is the size of this matrix? It's an n by n squared matrix, but how tall, wide is it?
10 by 10.
It is 10 by 10.
You have 10 roots, sort of, if you count multiplicity.
Right. The degree of this polynomial is 2 plus 3 plus 5 is 10. The characteristic polynomial, the degree of that is the size of the matrix. Is everybody okay with that? Okay, next question. What is the determinant? That's what P of X is, right? It's the determinant of A minus X. So what's the determinant?
Is it a squared times b cubed times c?
Um, what is equal? So. You gotta be careful about the signs, but you've got -1 to the third. So basically there's a -1 to the 10 power. Yes. Okay, finally. The last question is. Assume that A is diagonalizable. That's a big assumption, so that's going to help. Find each eigenvalue and the dimension of the corresponding eigenspace. For the eigenvalues.
A, B, and C.
The roots of the characteristic polynomial, A, B, and C. Everybody okay with this? Has multiplicity. 2, 3, and 5. Right. What are the dimensions of the eigenspaces? Correct. The dimension of the eigenspace has to be exactly the multiplicity of the root for A to be diagonalized, right? If any of those fell short, for example, if we only had a 3 or a 4 here, then the matrix would be diagonalized, right? So the diagonalizable is definitely needed in this. Is that clear? Everybody good? Okay, others. Yes.
Quiz 21 question 2.
Let's do today, at 8 o'clock. So I gave you some vectors here. And I gave you this list of 4 vectors. It says for what values of A, if any, do the vectors form a basis for R4? All right. You know what? I'm just gonna get on the horse and ride here. I just want to figure out how many data columns I've got. Yeah, this looks terrible. It's really not so bad. What for sure is not gonna work. This could be a basis. 0. So. You can throw 0 out because you don't have 4 pivots if A is 0 because you've got a column 0, right? Here's the key. Now that I know that A is not 0, I can divide out by it. So I can make this, I can reduce this matrix using no operations. 1, 1, minus 1, 0, 1, 0, 0, minus 2 A. Minus 1, 1, minus 1, minus 1, and 0, 1, 2 over A, 0. Am I okay with that? Yes.
You get the 0 in the first row of column.
What did I do? Oh,
0 in top right.
Yes. I made a mistake there. That should be 1, shouldn't it? Everything okay now? Okay. I'll use the top row to sort of take some stuff out. I'm not gonna go all the way. I'm just gonna go to where I can determine if I've got enough pivots. 0, minus 1, 1, and minus 2 over A. Minus 1. Minus 1. 0, 2. Straight up back, it's minus 2 zeros. And 0, 1, 2 over A. If you'll excuse me, I'll turn this to one. Right. And forgive me again. 0, 0. And I'm gonna do one more thing. I'm gonna minus 1 times this plus this. Yeah, there we go. Agree with that? All right. What do I need to make sure that there's 4 pivots? Only one thing is required. I need these 2 things to not be 0. That's it. As long as these are not 0, I've got 4 pivots. And notice these just vary by sign. These are essentially the same thing. This is just the minus sign of that. So I need, here's what we need for this to be a basis. A is not 0. 2 over A One is not zero. Or in other words. Minus. So as long as A is not 0 or -2, it's a basis. Okay, okay with that? Okay, the next question is, if you've got to go, that's cool, but I'll finish this one off. For what values of A do the vectors form an orthogonal basis for R4? Well, it's not even basis, it have that, so I can throw those out right away. But what do I need for it to be orthogonal? I need every possible dot product to be 0, right? Notice the product of these two is automatically 0 because it's A squared minus A squared, right? The product of these two is automatically 0 because it's minus A squared plus A squared. The product of these two, I get my dot product, I get 2A squared minus 2A. That's 0. Right. Product of this, the product of these two is 0 automatically, and also the product of these two is 0 automatically, and the product of these two is that's 0, and this one is, I'm sorry, this one is the same thing. So for orthogonal, if A is equal to 1 or 0. So orthogonal basis. Right, because if if you take 0, it's not a basis. So orthogonal basis, you need A plus 1. Pick an orthogonal basis that you found in part C and express vector as a linear combination. So our orthogonal basis is this. One minus 1 0. 1 0 1 1. Minus 1 0 minus 1 2. And 1 minus 2 minus 1 0. Right. And what we need to do is express, if I call this B1, B2, B3, B4, we need to express W, which is 7 5 11 3. In terms of this basis. Now, this would be an obnoxious problem if it weren't orthogonal. But here's a have W equals W dot B1 over B1 dot B1 is B1. W dot B2, B2 dot B2, B2, W dot B3, 3 dot B3, B3, W dot B4, B4 dot B4. And so, let me just stop the numbers here. W dot B1 is 2 so that is 1. B1 dot B1 is 3. That's vector. V1. 1 minus 1 0. W dot V2 is 18 and 3 is 21 over V1 dot V1 is 3. That's V2, which is 1 0 1 1 plus W dot V3 is minus 18 plus 6. It's minus 12. over, got that with itself, and it was 6. And finally. Dot right here is 7 minus 10 is -3, -14. Got that with itself, 6 again. That's the final right there, 7, 5. And as obnoxious as you may think that was, it's a lot better than saying the system equations figured out. Okay, questions on that? Okay, you all have a good weekend or get your quiz today, and I will see you on Monday.